Hello, everyone. This is Fabio Calefato from the University of Bari. I'm the session chair for this session. The session is titled Software Engineering for Machine Learning, Data Science, and Innovation. As you can see, hopefully from my screen, we have 4 papers in this session. We have 2 technical papers, 2 full papers, and then 2 emerging results and vision papers. Let me remind the authors of the time allotted to them. Technical papers will have 10 minutes for presentation plus 5 for questions, and vision paper should stay around 7-8 for the presentation, and the remaining time is 2. Hopefully speakers should try to stay on time, otherwise I have to jump in and remind and interrupt them during the presentation. So it's better for them to properly time. For the audience, please feel free to comment in YouTube, on Facebook, and I will manage to select the most relevant questions and show and ask them for you to the presenters. So I think we can start with the first paper. So the first speaker is Alex Serban. Hello, Alex, and he's going to talk about this paper, Adoption and Effects of Software Engineering Best Practices in Machine Learning. So, floor is yours.
Hello, everyone, and welcome to my presentation on adoption and effects of software engineering best practices in machine learning. My name is Alex Serban, and I'm a researcher at Radboud University in the Netherlands, and also at a company in Amsterdam called the Software Improvement Group. This study was done together with Koen, Holger, and Joost, which are researchers at Leiden University in the Netherlands. I think we all observed that machine learning receives increasing attention both from industry and academia, and that the adoption of machine learning technologies calls for mature engineering techniques to ensure these are built in a robust and future-proof manner. In this study, we aim to empirically determine the state-of-the-art of how teams develop, deploy, and maintain software with machine learning components, with the ultimate goal of creating a body of knowledge that can help practitioners to increase their development processes, but also to share their knowledge about developing software with machine learning components. Towards this goal, we mined both academic and gray literature and identified 29 engineering practices for machine learning applications. And in order to validate them, we conducted a survey with over 300 practitioners to determine the degree of adoption of each practice and to validate their perceived effects. Firstly, we ran a literature review on the topic of software engineering for machine learning, and we reviewed in total over 50 articles, both from academia and gray literature, on the topic of software engineering for machine learning. We observed that the majority of literature on this topic comes from gray literature, which is blog articles, presentations, or white papers from companies that developed or adopted these solutions. We compiled a curated list of articles, which is available on GitHub as an awesome software engineering for machine learning reading list. And from the literature, we compiled a catalog of 29 software engineering practices for machine learning, divided in 6 categories corresponding to the overall machine learning development process. We can see in the picture on the right that we have practices that are closer to the classical software development lifecycle, such as coding, deployment, or team, but also practices that are specific to machine learning and data science, such as data and experiment management. All the practices are available on our website, displayed here. In order to validate the practice adoption, we design an observational study, which means that we ask participants to fill in a questionnaire and answer if at the moment when they take the questionnaire, they adopt any of the practices that we presented. The questionnaire had a total of 45 questions divided in 4 sections. In the preliminary sections, we asked participants information about their background in order to assign them to groups, which made the study a concurrent control study. Afterwards, we asked practitioners and participants if they adopt any of the practices that we presented. The next section that we had in the survey, it's called effects, and allowed us to test the hypothesis that adopting a set of practices leads to an intended effect or to a desired effect. And ultimately, we had a section meant to evaluate the tool adoption for software engineering and machine learning and the confidence of the participants. We received in total over 350 answers, but after filtering them, we ended up with 313 valid answers. We can see that there are in total 4 groups, mainly regions or continents, organization type, team size, and team experience. We see in the first plot that Europe has a higher presence although other regions are also well represented. On the plots on the bottom, we can see the adoption of practices grouped by the four factors presented earlier. And in the first plot here, we can see that the adoption of practices is similar across regions, except for North America, which has a higher adoption rate. This means that Europe, although it is a bit overrepresented, it does not introduce significant bias. Further on, we can see that tech companies lead in practice adoption here, which is not surprising, since tech companies also lead in research, but also in development of many of the tools for software engineering and machine learning. And further on, we can see that practice adoption increases with team size and with team experience, which is again not surprising, because more team members means that more practices can be adopted by them, and also that with team experience, maybe the developers or the practitioners are aware of the practices. Overall, the demographic information from the survey shows that the questions were clear and they didn't introduce any significant bias. We didn't saw any anomaly in the data. We also evaluated the adoption of the practice adoption based on the data type. In the survey, we had a question regarding the data type used, and we had in total 6 data types, namely tabular data, text, images and videos, audio, time series, and graphs. We can see on the plot on the bottom that the adoption of practices is largely independent of the data type used, with a small variation for audio and time series, which show a relatively higher adoption rate. Although they, as we can see on the plot on the top, they are also less represented in our data set. We also omitted the graph data types, because we didn't have enough data. Our questionnaire is still running, so we hope that in the future we can collect more data about it. Based on the survey answers, which were the survey answers were on the Likert scale with 4 possible answers, meant to evaluate the adoption of practices, namely completely, mostly, partially, or not at all. So based on the survey answers, we ranked the practices with a ranking algorithm that we defined in the following way. We took the rank on completely, the average rank on completely plus mostly, and the rank on completely plus mostly plus partially. And then based on this, we averaged the ranks and we ranked the practices based on their adoption. We defined this ranking algorithm in such a way that maybe we can eliminate some of the noise that lies on the boundaries between the answers, or for practices that cannot have completely adoption. In the picture on the right, we can see all the practices that we identified, ranked by their adoption, starting with the most adopted on the top. We see that practices related to measurements and versioning are widely adopted. For example, capturing the training objective in a metric that is easy to measure and understand. At the other end of the spectrum, we see that the most neglected practices are related to feature management. For example, actively removing or archiving features that are not used, or assigning owners to each features and documenting their rationale. We also evaluated the relationship between different practices and effects in several ways. So in total, we have 4 effects, namely agility, software quality, team effectiveness, and traceability, corresponding to the groups of practices presented here. The effects are also mined from the literature whenever the authors mention these effects, and we can see that they are not directly applicable. So many practices apply in order to achieve one effect. In order to evaluate the relationship between practices and effects, we used 2 methods. The first one is we just analyzed the correlations between them, and we found out that the effects correlate very strongly with the practices. And secondly, we trained different machine learning models to predict the effects from the practices. And we can see on the picture of the right that we trained models with increasing complexity, from linear regression to random forest, and also with automatic hyperparameter optimization. And we see that the effects can be predicted very well from the practices. The mean square error is very small, and also the correlation between the predicted effect and the true effect is very high. We also plot for each effect the practice importance as revealed by these models, and also the adoption rate mentioned earlier. And we see that in the plot here, we see that an overview for which practice to adopt first in order to maximize the return of investment for achieving a desired effect, such as agility or team effectiveness. In conclusion, we surveyed academic and grey literature and identified 29 software engineering practices for machine learning. We validated their adoption and effects through a survey with over 300 participants and built an open source reading list and catalog for engineering practices for machine learning. In the future, we plan to extend the questionnaire with more practices and maybe create an assessment tools for team developing machine learning applications. Both the reading list and the catalog are open source and contributions are welcome. They can be accessed through these links here. You can feel free also to take the survey if you develop any application with machine learning. We also practiced a report based on this paper, which is available at our website. Thank you for your attention.
Thank you, Alex, for being perfectly on time. We have time for questions, so I will start. And I skimmed the paper during your presentation, and I was looking at your mining from literature, and I found a bit surprising. It seems like you in your query you did not include AI as a term. Am I right? Maybe I'm missing something. So I wonder if this was a conscious decision. There was a rationale behind this.
Yes, so we specifically omitted this term because it is very broad. So the discussion about AI also includes notions of ethics, for example, and notions of philosophy, and then the queries were very diverse. So we decided just to focus on machine learning, which is the main subfield on AI, and it's more about development algorithms and deploying them.
Yeah, okay. Good answer, thank you. So there's a question I'm gonna show and gone from Andrew. Often machine learning algorithms are implemented by small teams in dynamic programming languages like Python. Do you think that this impacts on the ability of teams to adopt certain best practices? Good point.
Yes, so the answer is that there is no impact from the type of programming language or the framework that is being used. The practices are more higher level. So there are things, for example, in the data management, there is a practice on continuously checking for distribution changes or checking for bias. So no matter which programming language or framework is used, these practices can be adopted.
Oh, okay. Okay, I think we can move on to the next paper. Thanks, Alex, again for your presentation. It was very interesting. I will make sure to read the paper at the end of the session. Thank you. Okay. So next presenter, I think it was it's Andrew Simmons. Okay, and welcome, Andrew. So he is going to present the paper Large-Scale Comparative Analysis of Coding Standard Conformance in Open Source Data Science Project. So it's a bit of a mouthful, but I hope I didn't botch the pronunciation. So Andrew, please go ahead.
Okay, so basically what this paper was about is we took open source data science projects from GitHub and ran them through Pylint, which is a code quality analysis tool for Python projects to check whether or not data science projects follow best coding standard practices. So if you've worked on a data science project before, or just written research code for that matter, you'll probably have noticed that data science code often doesn't follow best coding practices. It's quite exploratory, and as a result, we end up with code like this, with a lot of debugging done as print statements, magic numbers, and variable names that don't always reflect their true meaning. But rather than leave this as something anecdotal, what we did in this paper is a large-scale study to see whether we could find empirical evidence of this and to better investigate how data science projects differ from traditional software engineering projects. So firstly, we need a corpus of data science projects on the left there. And rather than come up with our own criteria, we used an existing list published in Mining Software Repositories 2019. But the issue is that it's not enough to just investigate data science projects, because take any random project on GitHub and chances are it's not going to have the best code quality. So on the right there, we also have a corpus of traditional software engineering projects where we took the original query used to select the data science projects from GitHub, inverted it to get everything on GitHub that's not data science, but still keeping the same quality criteria in terms of the number of stars and limiting to Python, which is the most common programming language for data science projects. An issue we ran into is that data science has become a lot more popular of recent, so it would make no sense to compare a young data science project to a traditional software project, and Python's been around for almost 30 years, so it could potentially be quite old. So to deal with this, we set a date threshold where we just took traditional projects since 2016 and an age threshold to make sure that both sets were more or less the same in terms of quality, in terms of the number of stars, and in terms of maturity when they were created, how old the project is. We ended up with two sets of data science projects and non-data science traditional software projects with about 1,000 code repositories in each. So how does the adherence from differ between data science projects and traditional projects? We ran both through Pylint, which is the Python code quality analysis tool, which does hundreds of different checks. Some are quite mundane, checking for conformance to the Python style guidelines. Others are more code smells, checking for things that might not be quite right. So the top three differences are shown here, and these are survival plots. On the x-axis is the number of violations or warnings per line of code. And on the y-axis is the proportion of projects that have at least that many violations. All you really need to know is to the top right is worse. So on the top there, what we see is too many locals and too many arguments warnings, where the data science projects had a lot more violations than the traditional projects. So these are things like functions with excessive numbers of variables defined in the scope of the function, or an excessive number of parameters. And it makes sense because machine learning is often dealing with complex algorithms. So a lot of variables. Ideally, you might say that ideally it should have been refactored out into smaller functions. And also they'll have hyperparameters which control the search for the best fit, and a lot of configuration options, causing these functions with excessive numbers of parameters. Down the bottom, we have invalid name warnings. Again, a difference between data science projects having more violations than the traditional projects. Triggering on things like using short single letter variable names rather than something more expressive, or using incorrect casing conventions, for example, uppercase for something that's not a constant. So we investigated a sample of these, and what we saw was in the data science projects, they were often implementing mathematical algorithms taken from papers. So if the paper was using mathematical notation and had a variable called uppercase K, that's also how it would be implemented within the data science code. There'd just be a variable named K, and it would be uppercase, whether or not it's really a constant. So I'm not necessarily saying that's the wrong thing to do. It makes sense that you'd want your code implementation to match up with the paper to make it easy to see the correspondence. But it is a significant deviation from traditional best practices that would be followed by a software engineer. So the final question we asked is, within data science projects, particularly the larger data science projects, where are these coding standards violations occurring? So what modules? So machine learning data science is usually actually just sort of a small part of an overall data science project. Around that, you're going to need traditional software engineering architecture to support it. So what we found in the top there for the too many locals and too many arguments is the violations were mainly confined just to the very core data science machine learning parts of the data science project, whereas the surrounding code and unit tests weren't impacted as much. However, down the bottom there for the invalid name warnings, where we're seeing variable names that don't conform to conventions. It's not just the data science, the core data science modules that are affected, that are using the libraries like TensorFlow, etc., but all the rest of the code, including unit tests, including surrounding code in the data science project that's not directly using any data science libraries, is also affected. So that's something interesting to know if you've got mixed teams of data scientists and software engineers. Sometimes the data scientists aren't going to follow traditional coding standards, but it's just going to be confined to the very core data science aspects. But others, like the variable naming, just spread throughout the entire project. So in conclusion, there's definite differences between how coding standards are applied within data science compared to traditional projects. And the differences aren't subtle either. For some aspects, we were seeing violations in the data science projects by a factor of 2 times as many violations per line of code compared to the traditional software engineering projects. That said, I'm not necessarily saying the violations are without reason. So as future work, what we want to do is follow up with data scientists to better understand why these violations occur, what coding standards matter to data scientists, and try and develop software linting tools that are better tailored to the needs of data scientists. Okay, thanks for listening, and if you have any questions, I'd be really interested.
Thank you, Andrew, for being on time and for an interesting talk. There's a question already in the queue, but I will start with one. I was curious, when you mentioned future work in the paper, also you mentioned doing some qualitative analysis. So I wonder if you can speculate more what you mean by qualitative in this case, what you're...
Okay. So for the paper, we manually looked at some of the violations that were picked up. But ultimately, I don't want to just say what I see. Ultimately, we want to show these to data scientists, to get data scientist feedback, and also compare that to how a software engineer might react, because ultimately data scientists and software engineers have to work together on larger projects.
Okay, and there is one question that covers the quantitative side instead. Luigi 40, does the linter you use really reveal also the presence of Python errors and warnings, or is it limited to code convention violations and code smell?
Okay. Yes, we're using Pylint, which does try to detect Python errors, but the problem is because Python's a dynamic language, there's a lot of false positives. Again, that's why we compared to the traditional projects to try and deal with the fact that some of the errors it detects are going to be false positives. But yes, it does try to detect genuine errors as well.
Okay, we have time for one last question. Okay, Christina, thanks for your presentation. Could you identify impacts of those violations in long-term maintenance data science project? Tricky question.
I'm not sure if this completely answers the question, but we also looked at other aspects such as how often the projects forked and how many contributors they had. So what we saw was data science projects usually had less contributors, but were forked more, which suggests that in contrast to traditional projects where everyone contributes to the same project and fixes the bugs, in data science, it seems like there's just a few contributors and everyone sort of forks the project and modifies it to their needs. I guess
it's okay to say you need to think about it.
Dimension that data science projects aren't necessarily maintained the same way as software engineering projects because they're being forked so often and modified rather than everyone contributing together.
Okay. In conclusion, have you by chance looked at how the violation change, checking the revisions on the same files, like if they go up and down and something like that?
We haven't looked at the project evolution aspect yet. But that's a good suggestion. Thank you.
Okay, thank you, Andrew. Nice presentation, nice work, and thanks again. So let's move on to the next presenter. We finished just with the two technical papers. Now we start with another two vision papers. Next presenter is Nauman Bin Ali. Hi, Nauman, thanks for being here. And he's presenting this vision paper, The Impact of a Proposal for Innovation Measurement in Software Industry. Just let me remind you, try to stick on 7-8 minute stops. Okay, thank you.
Thank you very much for the introduction. Just a clarification, it's not a vision paper, it's actually a reflection paper. So what we have done is we have reflected on a proposal that we wrote about innovation measurement in software industry. And that was a work that I did in collaboration with Henry and Richard. And now this reflection paper we've also done together. What we have done in this study is that we looked at the proposal of innovation measurement that we submitted to JSS. It was published in 2013. The contribution in that study was that we did a systematic literature review and we also did a survey in software industry of practitioners working on the topic. And then we synthesized the information and we presented a comprehensive definition of innovation. We presented a model where we identified different aspects of innovation measurement. And then we also had a proposal for a set of associated metrics that a company could use when they're trying to approach innovation measurement in their context. To look at to reflect on the impact of this work, we mainly relied on qualitative analysis of the citations to this paper. And the paper was received very well in the community. So far in January, when we did this work, we had over 234 citations to the work. It's also among the most cited papers in JSS published between the years 2011 and 2013. So it sort of indicates that the paper is perhaps received very well. In terms of looking at the demographics of the citations, we identified that 116 citations were from peer-reviewed papers which are published in English. And for those papers, the full text was also available. Those are the papers that we considered for a more in-depth analysis in this study. What is also interesting is that among the citing paper, 81 of the 116 are actually journal articles. So there are more journal papers citing our work. But we didn't just stop at the number of citations to the paper. we actually wanted to see how our work has been cited and used. So we looked inside these 116 peer-reviewed papers, how have they cited and why have they cited our paper. We relied on an existing taxonomy for analyzing citations, and this is work from Tupel et al. And they have 4 broader categories, and within each category there are certain nuances that they've tried to capture. So these 4 main categories in our case would mean that if a citing paper has identified a weakness in our work, if they have compared their work with ours, if there is a use or application of the work, or if they're built on top of our work, that those would be the first 3 categories, that is weakness, comparison, or expressing a positive sentiment about our work. And if we did not find any enough textual evidence around the citation to put the citing paper in one of these categories, we considered that a neutral citation. So we also did a pilot where 2 of the co-authors applied this citation scheme on 10 randomly selected papers so that we get a consensus on how we want to apply this. Then we applied this schema on the 116 full-text papers. We found that, interestingly, only 2 of the cited papers have a comparison with our approach and the results that we have presented in that paper. And there were no papers commenting or highlighting any weakness in our work. What was also interesting was that only, I mean, we have all the bias as an author, but we still didn't find enough papers expressing positive sentiment. And by positive sentiment, I mean that the paper has been applied in a use case, or so on and so forth. A majority of the citations were actually neutral. So 75% of the citations to our work are basically what we consider as neutral citations. Another interesting aspect was that the work that we presented was targeted for software industry. It's there in the title of the paper, and it's also published in Journal of Systems and Software. But we still get more citations from disciplines outside of computing. So there are 72 citations from outside of computing literature. We looked further into the 44 citations from the computing literature, and we identified a few interesting themes, which include the open innovation, role of innovation stimuli, and process models for innovation management. In our original study, we had an organizations-centric view, and I think it will be very interesting to see how innovation measurement can be handled in the context of open innovation, where you're actually going beyond the organization boundaries. Just to conclude my presentation, I would like to share some observations and also sort of a call for improvement. In terms of who cites the work, we also identified that as many citations are of our work in the gray literature, as many as we found in peer-reviewed literature. So I think it's interesting. There is a lot of work in the community on multivocal literature review. So I think this sort of validates that, yes, that might be interesting to look further into, but we did not do that in this study. Like I said earlier, that we found very few critique or weaknesses of our work. That could, of course, mean that the work that we did was such high quality. But I think another plausible explanation is just that there are so few comparisons and critical reviews that have cited our work. Yet again, the study shows that just the number of citations alone cannot be used as a good indicator of impact. And so I think that's well known, but it's good to see more evidence about that. Based on that, what we would also like to recommend is that we as a community have to promote responsible referencing, and that we can do by raising awareness, both in terms of when we are training our PhD students, when we are writing our own papers. We can also support the editorial process. And with that call for action, I would like to conclude this presentation, and I hope that we can take the rest of the time for the questions. Thank you.
Okay, thank you, Nauman. Thanks for being on time. So, don't see questions asked, so I will get started. So, first thing first, I'm not sure I get what you mean by responsible referencing. So, what you are suggesting? I mean, as a researcher, I'm interested in understanding what you're suggesting me to do.
Yeah. So I think what we have done in the results section, or actually in the discussion section of the paper, you have a paper which actually has a bunch of guidelines in what is responsible referencing. So typically you would ask yourself this question: am I actually just citing this work for the sake of citing, or am I actually building on top of it? Okay. So we have references where you're listed among 15 references.
Okay.
Something has been done about innovation in this paper, and then you get a citation.
It was more related to your work, but I get your point. Thanks. So there's other questions from other people. So let's start with this one. Heitor Costa, did you identify any computational tool to measure software? Don't know what actually. Not sure I get the questions now that I'm reading it. Measure software for what?
I'm sorry, I didn't understand the question.
Yeah, okay, let's move on, sorry. I think it's also typing again, so let's try this one. What do you mean by unwarranted citation?
So, for example, the very extreme example that I have is that we had 6 cases where the paper was listed in the references, but not cited in the text. I think that's a really extreme example, but we've had 7 or 8 of those. Then you also have citations where, and this is often the case in the related work, where the authors are not really critiquing your work, not really building on your work, but just listing you among all the 5 or 6 papers which have been about a certain topic. So I think there it's not really meaningful to have this citation to the work there.
Mm-hmm. Okay, one last question from me. So you said you noticed there was a lack of criticism. So on hindsight, if you were to write the paper today, what would you change in your paper?
In my paper, I think there is a whole bunch of things that should be
too many to say.
I mean, just a very concrete example. We only searched for journal articles in that paper, which is not the case in modern systematic reviews. I mean, we typically do also consider conference papers and so on and so forth. I think that was a huge restriction that we added, but no one has ever complained about it.
Okay, so that would be the one thing that you will at least change.
Sorry?
That will be the one thing that you will change at least. If you were to pick just one, that would be it.
I think there will be more, but since you
okay, thanks for that's very honest of you. Thank you. Thanks.
Thank you.
Okay. Thank you, Nauman, again. So time to move on the last presentation. The last presentation is presenter is Gouri Deshpande. I see him here, but not on video.
Hi.
I heard. Sorry, apologies. I cannot see you.
Yeah, sorry. For some reasons, my video stopped working just this morning. I don't know why.
Okay. So Gouri, she's going to present the paper Beyond Accuracy, ROI-driven data analytics of empirical data.
Yeah.
Okay, can you share the presentation, please?
Sure. Okay, you can see the screen. Hello.
Go ahead, Gouri.
Okay, fine. Sorry. Hi, good morning. My name is Gouri, and my co-author Guenther Ruhe. We have our presentation today on Beyond Accuracy, ROI-driven data analytics of empirical data. So basically here, when we have too much of data, we don't know if investing too much of time in finding or chasing accuracy is the only way to get more better with data analytics, or we should consider ROI as one of the driving factors in order to understand how much accuracy or how much performance we should chase. So that's the idea that we are trying to figure out in this paper. And in order to do that, what we did was we explored the papers that we have in the ESEM in the last 4 years. And in that, we found that about 73% of the papers had some form of, no, 27% of the papers had some form of data analytics in it. But then only 39% of those 27% had some mentions on cost, benefit, and details related to how much data analytics is good enough. But it was not one of the driving factors that was used in order to understand how far one should go. So what does data analytics include? It includes mostly data collection, data processing, labeling, modeling, evaluation, which are actually human resource intensive in terms of efforts and time. So how much data analytics is enough and when one should stop? When we want to look at the technology investment curve for ROI, it looks something like this. When the benefit keeps on increasing, the respective cost increases. It in fact hits the plateau once beyond some point. In fact, the cost benefit curve drastically saturates and does not pay off beyond certain point. So we hypothesize that ROI-driven data analytics helps to determine this break-even point of investment and thus optimizes resource spent in this process. So in order to understand or evaluate this particular hypothesis, we had this research question, which says, what are the benefits of ROI-driven data analytics in the studies focusing on requirement dependency analysis? So what is requirement? Requirement is a specification of the system which tells what the system should do. So if we were to assume that these blocks here are dependency are requirements, then they could have some form of dependency which could affect each of these requirements on each other, and these could exist in most of the requirements, but then there could be some requirements which are independent. So in the literature, there have been defined two various types of dependencies, and we are specifically focusing on requires type of dependency in this research, and the dependent and independent type of dependencies on the broader perspective. So in order to understand how ROI-driven research impacts the whole data analytics, we conducted two studies. The first one was the one where we compared BERT, which is a state-of-the-art language modeling technique for NLP tasks, with naive-bayes and random forest, which have been used in many NLP tasks in software engineering research so far. In the second one was comparing active learning with passive learning, which is basically a random sampling mechanism. And then we have we used Firefox data in order to check these two studies and various values, parameters, settings that we have. So as shown here, the first experiment showed that when we slowly increase the training set size, starting with the 20% to 80%, the F1 accuracy for all these three classifiers increased slowly, but then at some point it reached the plateau here. So of these, BERT, fine-tuned BERT and random forest fared well. So we compared, basically tried to see how random forest and BERT are going to perform when we want to evaluate ROI. So it showed that the increasing training set size, F1 improves, but the curve shows plateau. So we wanted to analyze and check how these two classifiers perform on the economical scale. For that, we used cost and benefit. I don't know why this is going so fast. So yeah, so we use cost and benefit calculations here for in order to compute the ROI. And the benefit was basically considering the true positives and false negatives, wherein we penalized the missing dependencies using some penalty factor here. And then when we look at the graphs, it was very interesting to see that the accuracy increased over a period of time with the increase in the training set size. But then the ROI drastically dropped beyond 20% of the training set size. So it shows that the for this particular random forest classifier, applying ROI argument, the learning stopped with just 20% of the training set size. And beyond that, even though the accuracy increased, it did not make sense investing too much further in acquiring this rest of the data for training. While for BERT, it was a little different. Here, we achieved the accuracy of 0.07, which was achieved at 20% for random forest, with the ROI of 3.7, but then only after this point, only when the data was at 60% or more, the ROI was more and F1 was drastically better. So it showed that the training set size of at least 20%, 40% or more was required for the BERT to perform extremely well compared to random forest. So let's look at the second experiment where we compared active learning with passive learning. Active learning is a mechanism where it acquires most most useful training samples using sampling techniques such as min margin and least confident. So what we wanted to check was it is already shown that active learning actually performs really well compared to random sampling, but we were here trying to analyze how good it is economically in the context of software engineering data. So in order to do that, we again computed cost and benefit using these two equations, where we have, because active learning is performed over a number of iterations with the different training set and same test set. So that's the reason we have considered different values for training and testing value completions for ROI. And benefit is basically over the changing F1 accuracy.
Gouri, apologies, you're running almost out of time. So if you could please speed up.
Yes.
Thank you.
So yes, thank you. So as shown here, for baseline, the immediately at the second iteration, maximum ROI was achieved for baseline with the accuracy of 0.6. But for active learning, at the third iteration itself, the ROI was achieved with the F1 of 0.8. So it showed that for both baseline and active learning had a best ROI performance in the early iteration itself. So going down the iterations did not make any drastic change and needed actually additional human efforts to reduce the effort to achieve the higher accuracy. So in conclusion, it was evident that increased ROIs is not the method to invest in additional effort needed in achieving it, because ROI is the one of the factors which could come into the picture to decide on how far one should go. So in fact, simplicity first is one of the rules that would something it would see. So beyond accuracy, reflecting on benefit, it is essential to investigate the investment is what we are looking at in further work that we want to conduct. Thank you.
Okay, thank you, Gouri, and thanks. And let me check. I don't see a question, so I will start one. I think it's an interesting idea to add this economical dimension to understand what is good enough. But I was thinking do you think that this approach is better when you are doing some sort of exploratory work? What happens when you have some sort of, I don't know, a benchmark where you know what the others are already doing? So you know there's a system or something, some results that are already the best, and you want to outperform those. Will this approach based on ROI work as well? What do you think?
Whole of this study is based on those parameter values. So I think this just acts as a soft guidelines and not the one which will decide the factors. So it is mostly acting as a information to be able to understand which way to proceed further. If you have too many criteria or too many algorithms to decide on. So yeah, that's the output it gives. Yeah.
So you don't see much problem in that?
No.
Okay. Okay. I think time is up. You're actually 1 minute late, but anyway, thanks for to the speakers, for everyone for being on time, and all the audience for listening. So this is the end of the session, and I think we're gonna be back in a few minutes for the next one. So thanks again for tuning in. Thank you.